Everyone, this is lecture number 16 E512 CMOS analog IC design, and today is October 3, 2023. So we were talking about various current topologies, right, which has two important specifications. Z out has to be infinity and V min has to be 0. That means you can also come here, right? You can write down, just keep it there somewhere. So these are the things which we are expecting from any current source, current sink, or any current. However, it's very difficult to achieve infinity. You know that we have various topologies are available. One of the simplest topology is this one. This looks very simple. However, when you are designing, it has to be important that you use multiplier. If there is some W by L, if multiplier 1 with some value of multiplier, you can, let's say, n times IREF, you can have it over here. If IREF is the current flowing from here, right? And in this case, you can find out the, R out, which is R0. If it is 1, then R0 1, and same way the output is VDS, right? Similar things you can find out for other, if it is cascode, triple cascode, and so on and so forth, if you have available enough headroom. By the way, do we understand this word headroom? So if you have enough available of headroom, that VDS values, then you can go for it. Same way legroom also, right? Zero side legroom. And so if you have available enough head, then you can apply the required voltages or apply the required topology, and you can work on it, right? Just maybe before moving to anything else, so this was the last topology which we are talking about, right? This is one of the useful topology in a case when we want stable supply for a given current, right? Because everything is depending on power, not only on voltage, not only on current, right? Or sometimes people are talking in terms of output impedance. For a given impedance, what is the current you can pump, right? So that is also the way people are writing down in different linear regulators or maybe power management units. Generally what happens, if we are saying this is the circuit and there is VDD. So VDD, if you are generating from inside or anywhere, there might be many problems in VDD. This VDD, I want stable one, whatever voltage I want, it has to be stable for any process voltage and temperature, right? So that is sometimes a problem. So there is one circuit called band gap reference. Generally, all the people who goes to analog domain in a company, generally before doing anything, they generally design band gap reference. They give some time to design band gap reference so that they can become expert on analog circuits. This is very simple one, not complicated. However, designing requires some sort of some of the things are there. I'll try to cover it at the end if possible, right? But before that, what band gap reference does, because it's very important to know that band gap of any of silicon. Do you know what is the band gap of silicon? 1.12 electron volt, right? So this circuit is the one. And by the way, this particular band gap voltage is actually even for a large temperature range also, something like this. Given temperature, the band gap voltage of silicon, we go to, let's say, minus 42 plus 125 degree. There is a minimum variation. So that band gap we are talking about. So this VDD, actually this band gap reference circuit is the one which makes sure that wherever VDD is required, let's say this particular place, you are going to have band gap reference, right? But band gap reference alone with respect to temperature may not be able to drive the circuit over here, because many PMOS are available on parallel. Each PMOS looking from source side, it's 1 by GM. So if there are, let's say, each one of them is going to give you the impedance of 100 ohm, and if there are 100 branches, it is 1 ohm, right, or less than 1 ohm. So this particular impedance is very, important to drive all the circuits. So what we are keeping another circuit which is called load dropout LDO, which has actually VDD for a given current, or you can say that given load. It does not change. That is what design. And one of the LDO design is over here, where what are you doing? If the current flowing through this one is IREF through M1, the multiplication of that current is flowing from here. By the way, this current topology, you can make many other topologies are available. If you want, you can use cascode, you can use self-bias, Wilson current mirror, whatever current mirror you like, you can keep it here. There is no restriction on that, because still we are designing a current and we need, better current mirror which is going to give you very high impedance and low VMIN. This is what we want, right? And that is not possible with just this one, but you can add few more if you want. You can add Wilson, you can add, but it depends on the availability of the headroom. Accordingly you can do that. So if you look at this circuit, if this is VIN, this has to be VIN only, right? And this is fixed to VIN. It doesn't matter what load you have. This is a load, right? What load you are having, it doesn't matter. And same way, if you look at our circuitry, this circuit, I have not drawn anything on top. However, for any load, current will remain same. It's not going to change. This is biased by a given current, and that current will not change for any load. Same way, the circuit which we have seen just now, this circuit, the upper part, for any value of load, the voltage does not change. Hence, voltage and current are actually remains same for any load, and that's the actually requirement. So wherever you need the stable current, you take it from here, and if you need the stable voltage, you take it from here, right? So accordingly you can use it, and that was like we are doing it. And the circuit where we have gain boosting technique, this circuit name is regulated current mirror, sometimes regulated cascode also, and many things you can call it, but all are similar names. So this uses gain boosting technique, right? So now these are the completion of the whole current mirror thing. So we have started from the simple current mirror which we have drawn just now, whose V mean value, read all of them as VDS set, and you know that what is the value of VDS set generally we should achieve, right? More than 250 millivolt. So ID versus VDS is going to give you, by the way, this is approximate plot. The actual plot might look like something like this. This is IV characteristic only. I'm drawing it as per our just requirement. So if you are in saturation mode of operation, so in saturation, this is 1 by R0, right? That's the slope, and that is going to decide many other things, channel and modulation, other things. You can fix it by keeping 3L generally, just to get rid of it, right? If you are using low voltage, or I would say the cascode or Wilson, right? So it is drawn over here like this. However, Wilson has poor resistance, output resistance than cascode, right? Triple cascode has the best one, or if you take more, you can have even better. However, you will not have enough headroom to do that, right? So these are the different things. We also studied regulated cascode, where you are keeping amplifier in feedback, right? So that's going to give you better value of resistance. Sometimes you can use low voltage also, where you have 2 VDS, sometimes 2 VDS plus, so on and so forth. You should not go beyond VDD. Anything is there, you should not go beyond that. So that is what these things are actually summarized, right?
So what is headroom?
Headroom is supply voltage, right? How much is availability of the value of voltage, right? Different voltages are available across any transistor. So you can give, let's say that VDS has 250 millivolt. If I am saying that I am going to use this one, right? VB1, VB2, VB3, and let's say this is VDD and this is V. What is the gain, by the way? Yugal, what is the gain for this circuit?
GM R1 1 by G. Looking from Oriel.
Abhishek, what is the gain?
Minus GM2 into RO4 parallel with GM1 RO1, GM2 R2 to GM2 RO2 into RO2.
Do not forget this, right? So if you are forgetting this, then you are out, right? Do not forget this. So if I keep it NMOS or PMOS, so if VDD is, let's assume that it's 0.9 volt. So is it possible to tune this circuit for a given values? I want to keep each one of the circuit in saturation. So is it possible? What do you think? Why? I should have asked the question, do you have enough headroom? No.
In their perspective, I'm saying.
No, I don't see enough headroom.
Means
Not
driving
okay.
current is not, driving voltage is not there.
How do you know that it's not sufficient?
Because there are 4 transistors
Hmm.
and minimum is 250.
Hmm.
For
Yeah.
So 250.
Yeah, it goes beyond 1 volt, right? Or because 250 is the
So it is
least value. It's not the value from this point it starts. Sometimes some of the transistor will automatically take charge 400 millivolt or maybe 500 millivolt, or depends
So headroom
what
has to be more than 1 volt.
so what value of voltages you are giving here, it also depends on that, right? So accordingly you have the availability of the headroom and legroom, right? So how much is available, that is the thing I was talking about, right? So that's the end of this particular thing, right? Current mirror, no problem, right? If you agree, then I can go to the next chapter. No, not. Okay, I'll start this one. Still it is So next chapter is frequency response. So now we are going to talk in high frequency side, not at low frequency, where you are going to see the capacitance also. Some people have written uh, the gain is minus GM times Z out. Some people, but at low frequency that's not true. At low frequency that's not true. So Z out in shunt with RO. Z out does not exist. It is infinity only, right? So that was the thing. But if it is a general question for any value, then you have to include that, Z out. So we are talking about that frequency response where we are going at high frequency side, not at low frequency. So we were using small signal. I'm again reiterate that what is the meaning of a small signal. AC response means it's all about low frequency. Low frequency is as low as 0. However, it's not 0. However, it's not 0. Okay, it's not 0 hertz. It might be 1 kilo, 100 hertz or something. It depends on the application wise, right? So some application, small signal AC response, like for EEG application or somewhere where the bandwidth is 100 hertz, and I'm talking about even lower than that one, maybe millihertz or somewhere. So it depends on the application. Some places where bandwidth requirement is terahertz, then this might be like kilohertz, even sometimes megahertz also, where the response is flat. What I mean to say, response is flat means if I have frequency with respect to magnitude. This is very popular plot, you must have seen many places. So I'm talking about the regime where the gain is flat. I'm talking about this particular region where gain is flat, and that is what referring as small signal AC response, where you are not going to see any pole or zero, right? Wherever the poles and zeros are coming, that is what now we are going to study, and then we are going to say that small signal high frequency response. Then you have to add this adjective before the frequency, that it's high frequency. We are talking about high frequency. We are going to go beyond this particular flat gain region, right? So that is what I'm talking about. Okay. So let's start with that. First of all, this is very important, and we have to always remember him because he is one of the godfather of this theorem. What he gave, and it solves many problems from solving anything. Otherwise, you have to take complicated circuit analysis to solve any kind of circuit. So just to get rid of it, what Miller has told. So Miller told that if there are 2 points x and y, and y by x is actually a gain. Understand? AV is nothing but Vy by Vx. If there is a gain between 2 points x and y, and if I am going to connect some sort of impedance over here, Z, then the current flowing through that one is Vx minus Vy by Z, right? One of them has been considered as minus. So if this is plus and this is minus, and if this is the direction of the current, then it has to be Vx minus Vy by Z. Okay, this is one thing. So what Miller says, he, or I would say that pi networks are easy to analyze with by observation directly, I would say, because this network is also easy to do that, but pi network is much easier, right? We understand what is pi network, right? We understand, Yugal,
Yes.
what is pi network?
Pi is a pi filter is there.
No, pi network,
sir.
not filter.
Not recalling this.
Okay, what is pi? Pi network. Look at this. The way pi is shown. Okay, so you must have seen like there are 2 points we have talked about long back, and if it is connected with wire transmission
That is
line,
pi filter.
then RC, nothing like filter. We are not talking about filter. It might be resistance also. If you remember, we made it like this,
Yes, sir.
and it's easy to analyze. But if it is something like this, right, then things are getting difficult, I would say, to analyze. So generally, we want to have the pi network, which is easy to solve relatively, right? So that's what Miller is saying, that I am going to give you the network which is lookalike to pi network, and that pi network will be useful to determine where the poles are or where the zeros are very easily. Okay, so if that is the case, what Miller says, do not see this circuit as like this one, but consider this circuit and this circuit are exactly same. You have studied Miller theorem, right? You people have studied Miller theorem, right? In analog course somewhere, in UG course, right? You studied or no?
Yes.
Okay. So no. So this is the very simple thing. It's not so much complicated. It's just referring to what you have studied. It is same thing. That Miller says that if this is the circuit, do not see this circuit, but its equivalent circuit will look like this one. Equivalent circuit will look like this one. And look at this one. Now can you see? This is pi network,
Yes, sir.
right? So the current flowing through this one was Vx minus Vy by Z. However, the current flowing through Z1 is Vx by Z1, and current flowing through this one is Vy by Z1, sorry, Z2. Notably, from this point, like the current which was going this side, there is no other branch. If I remove this impedance and keep it here, if I keep it here, then whatever the current was going this side, same current should come this side, and same is true for this one also. That is what Miller has seen, that the current flowing through this one and this one has to be same, and same way current flowing through this one and this one has to be same. What I mean for that is Vx minus Vy divided by Z is equal to Vx by Z1, and at the same time I can write down Vx minus Vy by Z is equal to Vy by Z2. So can you tell me what should be the value of Z1 and Z2? Can you find out Z1 and Z2 and give it to me? Values of Z1 and Z2.
Sir, gain is negative.
It is up to you. I don't know.
J by 1 minus A.
Sorry,
J by 1 minus AB.
Z divided by
1 minus AB.
1 minus AB. Okay. Right. So this is one answer. What about Z2?
Z upon 1 minus
Z divided by
1 minus 1 upon 1.
so AB inverse. By the way, what Santosh has asked the question, AB might be positive, might be negative. Okay. It will change the polarity, by the way, accordingly. Okay. So these are the answers. Keep it in your mind, and if you forget any time, any point of time, it's not difficult to derive them, right? It's very simpler. By the way, AV is nothing but Vx by Vy. Those who are not able to understand, then AV is nothing but Vx by Vy. One place it will become Vy by Vx, so that's how it will become AV inverse. Sorry, I made a mistake. Vy by Vx. Right? So that is what is there, and that is what Miller has told us. So let's keep this in our mind and let's use it wherever it's required. But before that, let's do some small exercise. So there is a simple question. can we decompose the impedance R1 in two different sides? Can we do that? Ritika, what do you think? Ritika, right? Ritika. So what do you think? Can we do that? Just now Miller has told something, right? Why no? Why no? Why no?
So, John assume
What do you think? What's your name?
Akash.
Prakash.
Akash.
Huh? Akash. Akash. So tell me, we can decompose or not? We can decompose or not?
No, because there is two paths, R2 and Y direction. And the previous one has only one direction. So might be different current.
Now tell me, can I decompose capacitor in two parts? If you are giving this answer, means you did not understand Miller theorem. Again, rethink. This same thing what we have studied, right, in the past. Adarsh, Adarsh, Ajay, yeah, Ajay. What do you think? Can we decompose? One answer we got, yes, we can. Sorry, no, we can't do that. What about capacitor? We can decompose. Now, like you like this or no? What do you think?
I think we can decompose the value.
Hmm?
Capacitor we decompose.
And again, I'll say that her answer was correct. You have to give me the answer why we can't decompose it. Abhishek, what do you think? Nirmit. Look at this. What? Okay. Now let's go this way. Somebody can reiterate the Miller theorem. Let's go this way. Pragya, can you tell me what is Miller theorem is in your language? No problem. Huh, what you understood?
So when there are two points x and y, there is one single impedance. We can say the capacitive resistance and whatever it is. It have both are sharing to each other.
Then there is some mistake. That is what I'm saying. Try to understand what we are doing. Anybody who knows Miller theorem correctly. Now, संतोष बता
सर एक्चुअली जब हम प्रूव कर रहे हैं तो बी बाई पे जो करंट फ्लो कर रहे थे यहाँ पे R2 ऑलरेडी कनेक्टेड है.
I asked you the Miller theorem, not okay. You have to take the lecture, then that's a different thing. You can take it after my lecture. Now tell me Miller theorem, Santosh. Miller theorem. Amit wants to say something. Okay,
Sir,
bata.
when the two x and y are not equipotential, so there
Very
is
good. Okay.
there is then that resistance should be what is it?
No, this is correct. But what else? That was the thing. Then look, still Miller is, he is God, right? We consider him like. What is the important thing? Can't you see that important?
Create equivalence.
Sorry, yeah, Aman.
Creating equivalence.
Miller theorem. I am asking Miller theorem.
Sir is splitting that.
Okay, when to use Miller theorem? Whenever there is a gain element between these 2 points, between x and y, there is gain. Or there is a gain element. Then if something is kept between x and y, it can be decomposed in Z1 and Z2 as follows. That is what Miller says. Or okay, let's go again. Go back to what. Okay, now why you can't decompose capacitor? Akash, no. Aman, what's your name? You told Ajay. Ajay.
We can decompose capacitor.
You are here, right? You are from Lucknow. झांसी ट्रेन लो यहाँ आ जाओ वापस okay so yeah Pragya what do you think can we decompose capacitor yes huh there is no gain right between 2 points so there is no point in discussing this you can't apply Miller's theorem in such kind of things go with the regular network theory concepts use it KCL KVL whatever impedance technique whatever you have done it so we can't decompose the impedance you can't do anything here let's go this way let's decompose this you can decompose or not even if it's minus look minus is also considered as gain okay so tell me if there is one capacitor over here understand I am keeping these as dotted line just to show that these are the parasitics actually the capacitor is between Vx and Vy only this is for our understanding and this is using Miller theorem so what are these capacitances what is C1
C into 1 plus A.
sorry
CF into 1 plus A.
CF into 1 plus A is it correct or
The negative-
what was the
negative and
what is Z1
Z divided
1 minus AB Z2 is equal to Z divided by 1 minus AB inverse okay is it correct or no is it correct or not correct right because impedance is 1 by 1 by j omega cf right actually in this case z so just keep those values over there and without frequency component you can get the capacitance right so c1 is cf times 1 plus a and what about c2
CF times 1 plus A.
minus is there so
Sir, no.
Hmm.
Sir, is Z2 I think in denominator A inverse minus 1 should be there.
sorry
In Z2 in denominator A inverse minus 1 should be there.
a inverse minus 1
Yes, sir.
which one is correct okay. I followed what this is copied from Behzad Razavi
A inverse minus 1.
this is the one I copied from Behzad Razavi I don't see it this is correct look at this okay okay so right
जब हम x2 y करंट एज्यूम करें हम vx पे vx by करें और z2 कैलकुलेट करने के लिए हम y2 x एज्यूम करेंगे करंट या सेम डायरेक्शन
there is current going from y to 0 right
लाइक मतलब जो ओरिजिनल सर्किट है उसमें y2 x जाएगा जब z2 कैलकुलेट
oh yeah
तभी शायद
yeah yes because then yeah you are right that was the mistake from my side yeah then here now this is fine huh?
this is considered
Hmm? Now this is fine thank you it came because of your actually answer anyway so this is what two impedances right okay so we got this no problem right absolutely fine it depends on the value right? or the input side capacitance is actually augmented and output side it's getting lower right this is similar to what you might have studied in feedback I don't know whether I'll have time to teach feedback but if I am not able to teach you then go to my previous course that is E203 analog circuit design that's available on my YouTube where feedback is actually there one chapter on feedback where there are some proofs are already given that if there is a voltage controlled voltage source if it is kept in feedback first of all voltage controlled voltage source has Rin of infinity and R out of 0 if you are going to keep it in feedback let's call it R in closed loop. This was open loop. So R in becomes augmented by A beta and R out getting decreased by A beta. By the way, A beta is, this is forward gain, forward path gain, and beta is feedback gain, and 1 plus A beta is a loop gain. Note that A beta is much higher than 1, so it is actually multiplied by A beta or divided by A beta accordingly, right? So what it shows, if you are keeping anything in feedback, if it is voltage controlled voltage source, your input resistance becoming more higher, right? And same way output impedance becoming more lower, or it's going towards 0 and this going towards infinity. And same as if I'm asking you, let's say if this is a current control current source, if I am going to keep it in feedback, what I'm expecting, first of all, input resistance and output resistance for current control current source, low and high, or you can say that infinity or 0. So what should be the closed loop resistance in your opinion? Divide by 1. Why minus? It has to be 1 plus, right? That was a mistake, right? Loop gain is plus. If it is negative feedback, if it is positive feedback, then both will be minus. So actually positive feedback we need to find out. It may not be only minus. It depends on different conditions. And what about R out? 1 plus A beta, right? Same way you can find out others also, right? So we are discussing this because this is going to happen. This is just to find out where the poles are created. For that we need to check all these things. So what I mean to say, if Vy by Vx, because this particular is a voltage control voltage source, right? If it is voltage control voltage source, if I am keeping that in feedback with a capacitor which is in negative feedback, I should see input impedance has to be improved and R out has to be decreased. This is what should happen, right? Because this is what happening. Can you see? Earlier it was just CF, however right now I am seeing CF multiplied with 1 plus A, and this is going 1 plus A inverse, right? So if A is infinity, C2 becomes 0 and C1 becomes very high. Right? This is just some philosophy I am giving you so that you can see those things, because it's a feedback circuit. It is also matching with our philosophy of feedback. Okay, let's go this way. Now, this is the real circuit. We are slowly moving to the circuit where between Vx and Vy there is R0. It's channel and modulation resistance, right? First of all, do you think we can decompose using Miller theorem? Can we decompose? What do you think?
Yes, sir.
Sure. Why?
Because it is gain.
Where is gain?
There is amplifier. Amplifier.
Where is amplifier?
MOSFET.
So what is the gain that you are saying? This MOSFET, okay? How much gain? How much gain you are seeing from X to Y? Ragya, what do you think? What is the gain between X to Y? Is there any gain? First of all, do you see any gain? Do not go with your friends who will say you might be wrong also. You might have your own thought. Okay. Srishti, what do you think? X to Y. Do we have any gain or? Palash, where is Palash? Okay. Yeah, so what do you think?
So it will act as a common gate amplifier.
So then tell me the gain. Tell me the gain from Vy by Vx. First of all, tell me whether the gain is plus or minus.
Plus.
Okay. And how much it is? Hmm? GM or not? Okay, but how do you find out GM or not? So okay, so maybe I'm not giving those answers. So Vy by Vx you can find out, and you can keep it here. Let's call that one as A, and tell me what will be the value of resistance. One is going here, one is going here. Let's call this one RO out, and let's call this one as RO in. I'm decomposing RO in two different sides. So what is RO in? RO divided by hmm? 1 minus AV. Okay, A. Okay, we defined it A. So not so difficult. Whatever RO out, AV, A. Now replace that A with the gain. Okay, I'm not giving the answer. It's very simple. Okay, so okay. So can you see that which kind of amplifier this was, and like this particular X to Y, which kind of amplifier it is? Common gate is which kind of amplifier? Uh, current control, current control, voltage source. Why voltage? Why voltage? Why do you think it's voltage? Okay, at this point of time, it's an offense, right? I'm not. I cannot go back and I tell you, right? It will take its space. This course has not taken its space till now, right? So please do not make such mistakes. Okay, is it current or voltage? It's current. Okay, because output resistance is RO1. RO is actually very high. Anyway, so if we are going to keep this current control current source in feedback through resistance, what do you think? What are you expecting? Input resistance has to improve or has to what should happen in your opinion? Should decrease, right? In closed loop it has to decrease, and output resistance has to, that is what happening or not? You just see that, right? By the way, loop gain is much higher than 1, so of course 1 minus A is equal to minus A, and so R out is actually R in is decreasing, and A inverse goes upside, so you're going to see high resistance, right? So this is what happening, right? So you can decompose. Note that we are going to use many things later on. We are going to decompose capacitors also, so that it will be in a required in a required value, and you can see the poles and zeros directly. You should see that. Okay, right? This is very simple, right? This is same what we were talking about, right? By the way, I am following Behzad-Razavi. For this chapter I am following Behzad-Razavi. Okay, now let's go for this one very quickly. Somebody can volunteer and tell me what is the Vm by V in Laplace domain. Hmm?
One plus R is
Okay, so where is the pole location? Right, in hertz this is the place. In radian per second, 1 by rs times cm, right? This is easy, right? Okay, so this is the pole location. Okay, but the important part is sometimes people don't write minus, because we are going to plot something called magnitude plot. So magnitude is actually, we are interested in mod of the transfer function. And in mod of the transfer function, it is actually like this side. It will come this side. Somebody can comment on the what should be at the left side. How the frequency response should look like if the frequency is in negative. it has to be identical. Right? By the way, this is a low pass filter, but all signal processing people call it something else. Some low signal processing people are here. Some people who came from signal processing. So what do you think? What is another name? It's known as a brick wall filter. It looks like a brick wall. Right? That's why they call it brick wall filter. Depending on the slope, they don't call it. This is like this. They call it brick wall filter with infinite slope. Anyway, so we are interested in positive side. That's why we are drawing only in the positive side only. Okay. So you can call that value positive side also if you want, because we are interested in finding out this mod we are drawing with respect to frequency, not the negative side. But negative side is always identical. Some places are there where negative side is not identical. So we are not talking about it, but that's part of DSP or other advanced courses where you can study that, where negative side is not exactly identical, where it's not brick wall. Okay, no problem, right? This one very simple. Transfer function we found. Pole location also we found. Okay, let's go this way. So you have to answer 4 things. Find the transfer function of the circuit. Very quickly. Tell me the transfer function. Overall V out by V in.
One upon 1 plus S RS CD into given top.
Let's keep it this way. Even with
Into 1 upon S R1 secant into 1 plus S R2 secant.
right? It is simpler, right? Very simple. So now, okay, find the pole locations. FP1
Minus 1 by 2 by RS CD.
in same way you can write down others, right? Okay, now the question is what is the role of A1 and A2 block? What are the roles? What do you think? A1 and A2, if we do not keep or if we keep, what is the difference? Hmm. Okay, that's one reason. Okay,
Provide high impedance
provide high impedance.
to M and N node.
Okay, so what is the advantage in that case? Let's go this way. Let's remove this A1 and A2. Just remove it.
I think then we won't be able to multiply.
So directly you can't multiply, right? So the good part of this A1 and A2 are they are like a shield between two stages, right? You can actually write down different equation on kept it on pi network. However, if you see something like this, let's say, what are you going to do? You just take this capacitor over here. If the value of the capacitor is C2, can you tell me now new transfer function?
Plus
Let's take okay, let's make it a little bit even simpler. So first one will be same. Second one, Cn plus other side, right? Simple, right? So this happened because Miller was there, and afterwards this pi network was there. Let's go this way. Okay, same thing. You understand its importance also. Let's assume that okay. Now tell me, location of poles. First location of pole, F1, FP1, or let's call it FPM. So the pole available at M node without looking at anything else. Minus 1 upon 2 pi. Let's wait, okay, for others also. You might be learning this course third time, after BTech, MTech and PhD, right? So let's give chance to those people who are studying second time. Okay. Let's not use ball pen. Pen is not required, right? Why pen is required? By the way, we understand that if these C1, C2 are not there, then the frequency is 1 by Rs times Cn. Or whatever the resistance available here at this node, look at that. I am seeing two branches. Can you see two branches? One goes this side, one goes this side. Resistances and all capacitances are 0 at that time. So what I am seeing, by the way, at that time when I am doing this, voltage is again like it is also going 0, right? So there is no voltage source goes to 0. So in that case, what resistance you are seeing? Rs in shunt with A1 input impedance is very high. It's a voltage control voltage source, right? So only Rs. And at this node, how many capacitance are you seeing? One is seen, one is coming because of C2, one is coming because of C1. So tell me, what is C1? A1, right? Okay, A1 and A2. A1 and A2, right? True. Same way here, C2, 1 plus A1, right? If this is the case, right, then what should be the pole frequency at M?
C
Right. Fine. No problem. Now can you tell me what is FPN? Narmit, try FPN.
FPN.
N. At node N.
So minus 1 by 2 pi.
Okay, very good. How many resistances are you seeing?
R1.
R1. Okay, very good. Times. How many capacitances are you seeing?
Plus Cn.
Plus.
Say 2 to 1 minus A1 inverse.
1 plus A1 inverse, right? Plus nothing else, right? Now somebody else. Pragya, can you try for FPP? C1, okay.
C1 into, sir, if A1 and A2 are positive, also it should be
They are
C1
positive.
plus, sir,
Okay.
in the last bit, CF into 1 plus A, that
Oh, everywhere it has to be minus, right? That is what you are saying. Please correct them with minus. That's correct. Thank you. Right? So now tell me.
C1,
Hmm.
1 minus A1, 1 upon A1 into A1 A2 inverse
Okay.
and plus CP, RCP into
That's it.
CP.
That's it. Right? So you can see three poles are there. Right? You have to see which one is going to contribute more or high. That will come when we are going to do the real circuits where we know the value of these capacitances, so that each one of them will place themselves such that it's going to give you different, location, and other than that, not only this one, we need to look at the phase also. So we'll study that maybe Thursday. Okay. That's all for today. Thank you.